Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today in this video we will be talking about passive filtering.
We talked briefly before about impedance and how that can be used with passive circuits to analyze those circuits. Today I want to go into that in greater detail, and I want to talk about generic responses in a passive circuit. So let's again define a passive circuit is one that only has independent sources, resistors, inductors, and capacitors. In contrast, an active circuit has at least one amplifier element. Usually that would be a transistor, but sometimes vacuum tubes are used as well. Vacuum tubes are only now used for a very few special cases like high-end audio. So we can define an amplifier element as an element that can control a current via a control current or a control voltage. This is where we came up with the concept of dependent sources. So we had dependent current sources and dependent voltage sources. Those dependent sources are used as models of these amplifier elements. So, the fundamental theorem of electrical and computer engineering relates the input to the output for linear circuits. This can be stated, if the driving force to a linear circuit is of a sinusoidal form, x of t is equal to a times sine of 2 pi ft plus theta, then the output is also a sinusoid of the form a times the magnitude of h at j pi 2 pi f times the sine of 2 pi ft plus theta plus the angle of h at j 2 pi f, where of course h is the frequency response of the circuit. So what this means is that if we put a sinusoidal input into a linear circuit, we are going to get a sinusoidal signal out, and that output can be written based on the input form and the frequency response of the circuit. Fourier showed that any signal x of t can be written as a linear combination of sinusoids. This representation is commonly called the Fourier transform. Based on the fundamental theorem of electrical and computer engineering and this concept of Fourier's, we can write the frequency response of a circuit by adding up the responses for all the different sinusoids. And this is a critical characteristic of every circuit. Okay, let's look at an example. So we have an independent time-varying voltage source, V sub t of t, in series with a resistor and a capacitor. Now notice that the source is of the form, we have an ideal source and then we have a Thevenin's equivalent resistance. So this is a Thevenin form input circuit, okay? And now we can do a loop equation. And of course, we're going to do it in the S domain. So we would have minus Vt of S plus I out of S times RT plus C plus 1 over SC is equal to 0. We can rearrange this equation to get I out of S is equal to Vt of S over RT plus 1 over SC. We can also use Ohm's law to write V out of S is equal to I out of S times 1 over SC. And that's the second equation here. So we can then rewrite the first equation to solve for I out. The second equation to solve for I out, and we get I out of S is equal to SC times V out of S. We will then take this equation I just rewrote and plug it into the first equation. And when we do that, we get this first equation, Okay, I out of S is SC V out of S, and then when the right side remained the same, we can now find the ratio of V out over VT, and we end up with 1 over SC times the quantity RT plus 1 over SC. We can multiply through by the denominator, and we get V out over VS, V out of S over VT of S is equal to 1 over SCRT plus 1, and this will be a low-pass filter. You will not be able to tell that by looking at it unless you've had some experience, but we can look at it further and find that out. So we'll take our H of S that we had from before, right, which is 1 over SCRT plus 1. Okay, we'll plug in S is equal to J omega, and we get this equation. We can rewrite this in a number form for a complex number, because now this is a complex number. It only depends on omega, but we will look at a particular value of omega. So we can write this in the number form as the magnitude of H of J omega, which is this, times E to the minus J tan inverse tangent of omega C RT. So for convenience and a little bit greater understanding, we're going to let omega naught be 1 over RTC and rewrite the equation in this form. So now you can see that this omega naught, which is the natural frequency of a circuit, is kind of integral to what's going on at the circuit at any particular function, at any particular frequency. Okay, let's take that same circuit and look at it in a different way. This time, let's consider the output to be the voltage across the resistor RT. Now, some things are going to change and some things will stay the same. If we, again, write our current equations for the circuits, we can do a loop equation and solve it like we did before. We will come up with the same current I out of S. But now our output voltage is across the RT resistor. So using Ohm's law, we can say V out of S will be equal to RT times I out of S. So plugging in and rearranging, we can come up with V out of S over VT of S will be equal to SCRT over 1 plus SCRT. So what has changed? The output equation has changed. The current didn't change. We didn't change anything in the circuit, so the current couldn't change. Okay, let's now substitute J omega for S, and we get H of J omega, the frequency response, will be J omega CRT over 1 plus J omega CRT. We can write this as a magnitude and an angle, okay, that depends on omega. And it turns out that this is a high-pass filter. We can actually tell this. It's kind of a rough check, right? We can figure this out by looking at what happens when we plug in 0 for omega. So we plug in 0 for omega, we get 0 over 1, square root of 1. So that means that H of J omega will be equal to 0. Okay? And as omega approaches infinity, I write it's equal, but we know that it approaches. Okay, so the math is a little casual here. We plug in infinity. We end up with infinity over the square root of infinity squared. Okay, use L'Hopital's rule, but what you can tell is that this H of J omega will be equal to a constant. Okay, and that constant is going to be 1 over the square root of C times RT. You can also use MATLAB to calculate the frequency response. Okay, let me show you real quick though what this is going to look like. If we have J omega going here and the magnitude of H here, what we know is that at 0, it's 0. At an infinity, it goes towards some constant. So it's going to look something like that. Okay, it's rough. It might actually look like this. It might actually look like this, but the basic idea is that as we go toward infinity, it's approaching a constant. So this is the important result, and this is a little bit different from electrical computer engineering than it is for other fields, okay? Basically, we can build a circuit, and that circuit topology does not determine the type of filter that we have. Instead, the topology is dependent on what is the defined input and what is the defined output. And that is what determines the type of filtering. So this may seem a little odd when you compare it to different kinds of structures, right? But it is the relationship of the current voltage that is going to define the type of filter we have. So now let's consider a more general circuit. Here's a circuit with an ideal voltage source in series with a resistor, an inductor, and a capacitor. So if we call the looped current I of t, then we can write an equation for that loop, and we will write that in the S domain. So we have minus Vs of t, Vn of s, plus I of s R plus I of s times SL plus I of s times 1 over SC, and that's equal to 0. Okay, ran out of space a little bit, but that's okay. So we can take this equation and rearrange it, and we can come up with I of s is equal to Vn of s over R plus SL plus 1 over SC. So notice that for convenience, we are not writing I of s and Vn of s. That really, I think, can be somewhat confusing. So it's best just to leave it off now that you feel comfortable with the idea. So then we can write let's multiply 3 by SC, multiply the numerator by SC and the denominator by SC, and we end up with SCVN over S squared LC plus SCR plus 1. And this is what I generally do. I clear all the fractions in the denominator. So now let's just look at all the different outputs we could define. If we put the output across the resistor R, okay, then we can write I is equal to V out of R. And so we can plug in for I and then find the ratio of V out to Vn, and we end up with R over R plus SL plus 1 over SC, multiply by SC over SC, and we get SCR over S squared LC plus SCR plus 1. Okay, so if we look at the gain, when we have, let's say omega is equal to 0 will mean that S is equal to J omega, which is equal to 0. So we're going to plug in a 0 for S. So when we plug in a 0 for S, we have a 0 over 0 plus 1. So it's 0 over constant. And so that's going to give us, I'll just pull a sketch. That gives us a 0. We have 0. Now let's consider what happens when omega approaches infinity, which means that S approaches infinity. Okay. So we end up with infinity over infinity squared. And so we can see that if you use L'Hopital's rule again, you will see that this also goes to 0. So what we have, there we go. So that means that we start off at 0, we end up at 0, and somewhere in between we go up. And so that is what we call a band pass filter. Again, you could go into MATLAB and plot this and see that this is the case. If instead we look at the voltage across the inductor as our output, right, that means that V out would be equal to I times SL. When we substitute that in, we end up with H of S is equal to S squared over S squared LC over S squared LC plus SCR plus 1. Okay, so let's do our quick check again. When omega equals 0, we have h is equal to, let's see what that is going to be, 0 over 0 plus 1. So that's going to be 0 over 1, which is 0. When omega is equal to infinity or approaches infinity, we have h is equal to infinity squared over infinity squared. You can use L'Hopital's rule and you will find that that is a constant. Now, I didn't bother to figure out what that constant is because I don't need to sketch my circuit, okay? What I'll have is that at omega 0, okay, this is omega, this is magnitude of h. At omega 0, h is 0. At omega's infinity, it goes up to some constant, so we have something like this, which is a high-pass filter. Okay, now let's look at the voltage across the capacitor. Again, the voltage across the capacitor would be equal to I times 1 over SC. Plug that into our equation. Get rid of the SC by multiplying by SC over SC, and we end up with this transfer function. Let's look at what happens for omega 0. We have 1 over 0 plus 1, so that's 1 over 1. H is going to be equal, and I should say magnitude of H is equal to 1. For omega approaches infinity, we have 1 over infinity squared, which means it's going to approach 0. Okay, so sketch that out. That means we're going to start off with, at 0, we have H is 1. And then at infinity, we go to 0. So that's a low-pass filter. Finally, let's do something different. Let's look at the voltage across the inductor and capacitor combined together. So what that means is now our voltage is going to be equal to I times that series combination. So SL plus 1 over SC. We could substitute that into our transfer function, clear the denominators, and we end up with this expression. And if we put this together, let's see what happens. We have for omega is equal to 0, we have 0 over, we'll have 0 plus 1 over 0 plus 1, which will be 1. Okay. Omega approaches infinity, we'll have infinity squared over infinity squared, use L'Hopital's rule, and you'll find out that that also is going to be equal to a constant. And again, I didn't really worry about what the constant is. I actually think the constant's 1. But you don't have to even think about that. Just knowing that it's a constant's enough to get a quick feel of what's going on with the circuit. So if we plot magnitude of H with respect to omega, we start off with 1, and we end up with a constant. Okay, so that means we're going to go down something like that. Okay, and that is what we call a band stop filter. Okay, because it stops the frequencies in that band. So we've done several things today that were quite important. We practiced solving a passive circuit and solve for a gain. We looked at how we could determine the circuit's frequency response. We can do a rough estimate by seeing what happens when omega is 0 and also when omega approaches infinity. You could also put it in MATLAB for a precise response. We also talked about the fundamental theorem of electrical and computer engineering, which says that a sinusoid is passed through a linear circuit with its magnitude of phase altered by the frequency response at that particular frequency. And I didn't do it for you, except for I showed you some plots, but MATLAB will do these computations for you.